Alex is an assistant professor in the Department of Chemical and Biomolecular Engineering. His research combines chemical engineering, computational optimization, and uncertainty quantification to enable principled molecular to systems engineering of sustainable energy and environmental technologies. The title of his talk today is Design and Optimization of Integrated Energy Systems. Let's welcome Alex.
So today I'd like to tell a little bit of a story about how we can use systems engineering to think about these integrated energy systems that combine a lot of different possible energy conversion technologies to address renewables and integration. This work is part of it's funded by two big DOE projects, IDEAS and Dispatches as part of the Grid Modernization Initiative. But before we get into that, I think it's helpful to kind of say what my research group does. So I'm a chemical engineer, but I would also say I have a foot in the door of applied mathematics and I have a foot in the door of systems engineering. And what my group thinks about is how do we use mathematics and modeling to accelerate what we call molecular to systems engineering. So as a chemical engineer, I can think about molecules that enable new materials, that enable new devices, that enable new systems that have impact on the infrastructure scale. And this is horrendously complex. So in this diagram, it's just a tangled mess of how do you go from different possible devices and integrate them into systems. And what my group does, we use modeling and optimization to directly address this complexity. So we'll use tools like materials informatics to think about building predictive models. We'll use design-it experiments to think about how can you conduct experiments in the lab, or our collaborators do, that give us the most information. And then how do you use optimization to choose a bunch of to choose various different technologies to integrate together. And we think about uncertainty and how it propagates through all of this. Oh, yeah. Okay, is that better?
You can click it. Thank you.
All right, is that better? Okay. So we express everything in the group as an optimization problem, and we apply it to a lot of different things. Ting-Fei Liu is going to talk about this project on additive manufacturing later this afternoon. I'm going to focus on grid integration in energy markets today. I think if I stand near this, we get interference. So you probably have some notion that there's a lot of challenges with thinking about a highly renewable electric grid. And what this plot here shows is about over the course of the year, variability in generation in a bunch of different technologies: natural gas, coal, nuclear, hydro, wind, solar, and other. And this variation isn't just seasonal or annual, it actually happens in the daily level. So this is kind of the famous duck curve. If you squint, that kind of is the head of the duck. And what this curve is are kind of an average for the amount of power needed in California in megawatts for a day. So this is time, midnight to midnight. And each line on the curve is kind of the expected average. This is 2013, and this is 2020. This is an old curve. And you see this kind of decrease around 2 p.m. gets more and more extreme. That's because of solar. How do you deal with this variability? And in the US, we kind of have this patchwork of regulations by states. Many states have renewables mandates. So there's a lot of technical challenges coming. And a big question is, how can integrated energy systems help? So what are integrated energy systems? They take multiple technologies and multiple energy sources: nuclear, gas turbines, fossil, solar, wind. They combine them in ways that are synergistic, and you can produce multiple products. You can produce electricity, you can produce ancillary services that help balance the grid, you can produce chemicals like hydrogen, or you can produce heating and cooling. And what's really cool about integrated energy systems is they provide a lot of operational flexibility to help counter the variability of renewables. And because they have multiple profits, they also help make these systems economical. And to understand kind of the complexity here, we're just going to look at some data from California. So here's a map of California. There's about 8,000 dots on this map. Each dot represents a node in the transmission system for the electric grid in California, and prices are set individually at each node. Really cool optimization problems on how that's done. We don't have time to get into that. And then if you zoom into each node, actually prices in California are set at 3 levels. So the dollars per megawatt hour are set in the day-ahead market in hourly intervals, a real-time market in 15-minute intervals, and also the 5-minute intervals. And shown here are histograms of these prices over a year in California, and we can see as we go to a faster time scale, this distribution looks a lot less normal, becomes bimodal. And if we look at this time series over a week, the colors are the same as above, we see there's a lot more variability in this 5 to 15-minute time scale. We'll come back to that in a minute. You can also do some cool Fourier analysis that essentially says most of the variability is within a day. So if I'm thinking about energy storage, how do I take advantage of this variability? So you can set up an optimization problem where you want to design an energy storage system, say a Tesla power pack, you want to size it correctly, where it can interact with the electric market in California, either buying or selling energy, or providing these ancillary services at the faster time scales to help balance the grid. And the goal is we want to maximize revenue, right? Because everything needs to be profitable. And the decision variables are how do you participate in the market, and there's a bunch of constraints related to the technology of the battery. I took out almost all the math from this talk. And we could get some really cool results. So what this plot shows is the payback period in years, and this shows the storage size, so 0 hours of storage to 6 hours of storage. And this legend is encoded where a 1 represents yes, I'm participating in that market, and a 0 represents no. So this plot's really informative. So if you were to build one of these batteries and only participate in the day-ahead market, so that's only the hourly, and you're owned it by energy, your optimal size is about 2 hours, but it's going to take you 60 years to pay it back. So that's not going to work. But if you transact some of these ancillary services or go with the faster time scales, these lines get much better to where the payback period becomes a year or 2. Okay, now that actually makes sense. The other really interesting thing is the optimal size is smaller, like in the minutes to hour level. Why? Most of the market signal is at this really fast time scale. It's at the 5-minute time scale, or providing these ancillary services at the seconds time scale. There's a lot of data, and you can pull data from every location, and then you can look at, well, how does the payback period vary geographically? And what's really interesting when you run this analysis, you find in Central California, you have the shortest payback period. And then you can start to ask really interesting questions and say, well, these are the incentives that are being presented by the electric grid. Is Central California optimal from a really big systems perspective, or is there a market incentives problem? I'm not going to dive into that. Okay, so that's at a really big picture, but I think most of the people in the room probably care more about materials or devices. How can this analysis inform that? So here we're thinking about, well, what's the relationship between sizing, degradation, and how you replace these batteries? I'm going to switch from the Tesla power pack to the sodium-sulfur battery, which is a little bit lower round-trip efficiency. We did this work a couple of years ago. At that time, I was able to find about 4,000 cycles to failure in literature. And you can look up prices for this system. And what we're going to do is take this optimization problem, but we're going to add degradation to it. So as you charge and discharge, you lose a little bit of capacity. And we're going to see how this compounds over time. So we ran this analysis, and there's a lot going on here. Let me just dig into this. So we considered 4 cases. If I have no degradation, that's very ideal. If I have medium degradation, which it kind of got from literature is these 4,000 cycles, and then did an order of magnitude. We could probably have a really strong debate
as to whether this is 4,000 or 5,000, so we just did an order of magnitude. So that's the 4 colors. And then what these plots show are the net present value in millions of dollars. And these are organized by, am I only selling energy, am I selling energy ancillary services, and am I in only the day-ahead market, am I in the real-time market, or am I in both markets? So what do we see from this? You can't just transact energy in the day-ahead market. That is going to give you a negative net present value. You never get capital. You never get a bank to give you a loan. And the other interesting thing is when we jump to the real-time market and sell both energy and ancillary services, the net present value jumps up. Here showing the optimal battery capacity, so how many hours of storage, interesting, less than 1 hour. And this other super interesting thing that I love about these plots is these are showing orders of magnitude change in the degradation rate. And these plots aren't changing that much. So this actually helps us understand how important new materials kind of abstracted away at a degradation rate are. And in this specific problem, that is not the rate limiting issue. And this is just the power of kind of systems analysis. We can also then say, well, when do you replace? And we can look at profit per year scaled by replacement. And what we find is really interesting. There's just so many degrees of freedom in how you participate in the market. If you want to push out your replacement time, you can do that by just being a little bit less aggressive, and it doesn't impact the economics that much. So that's kind of a perspective on how you can take data in simple systems models and think about optimal sizing of energy storage, and you maybe even get into some material properties in a very abstract way. So this was a very process-centric analysis. So we had a detailed model for our energy system, and we kind of treated the electric grid as this cartoon infinite bus, where we got prices and it would always take our power. Kind of on the other side of the barrier is the power systems engineering community. And they were very focused on how do you model the electric grid, but treat all of these energy systems as little cartoons with very simple linear models. And in my experience, because I kind of play on both sides of this fence, there's a pretty big barrier. These communities don't talk really well. So we're going to talk about breaking down this barrier. So as part of this IDEAS project, we're really interested in breaking down that barrier and having really high fidelity process models, a lot more sophisticated than the battery model I presented, taking detailed grid models and understanding how they interact. So we came up with this multi-scale simulation work, which I'll describe in a minute, that couples these types of models. So this allows us to understand how dynamics and capabilities of these types of systems interact with the market. So we can go beyond like common assumptions like price taker. We can take a postulated new technology and we can understand how it's going to impact the market. And then finally, we can take these models and we can kind of set performance targets for these new technologies. So what we did is we came up with a framework where we can integrate really detailed process models with simulations of an entire market, this price setting process. So the way this works is you have some type of forecast for what market prices will be, and then we take our detailed process models and we solve an optimization problem that generates how they bid into the market. So how are they going to express their costs and capabilities to the market? That then gets sent into Prescient, which is an open source production cost model. Prescient takes all the data from every power plant in a region, and it's going to then determine the optimal schedule for the next couple of days. That then generates a dispatch signal, which then gets passed to our detailed process model, and then we can solve a sometimes nonlinear model predictive control tracking problem and say how would the system and maybe its storage be exercised in a way to track these grid signals, and then money drives everything, calculating how much the resource would make.
So one just interruption.
Yeah.
So when you put health in the system, right?
Yes.
Are you looking at the overall grid resiliency or?
Health here is actually looking at equipment health.
Okay.
So how aggressive do you want to be with your batteries, or how aggressive do you want to be pushing your gas turbine? because there's some trade-offs in how you operate and then the stresses that you induce.
But the resiliency is a separate aspect that you are.
Yeah. That's like a dimension coming out of the board. So we have interest in that. That's not captured here.
Okay.
It's a little bit in here that's in the weeds.
Thank you.
Good question. And feel free to yell them out. Like, interactive is good. So we could then take this framework and say, all right, what happens if we take this prescient tool that simulates the market, we take this representative grid, and we take a existing generator and we augment it with energy storage. How does that going to change the overall operation of the grid, and how does that change the operation for that specific unit? So we set up this case study with this open test system. It's actually really hard to do this analysis with real data because this real data is protected for a variety of reasons. It's proprietary, it's sometimes considered critical infrastructure data. That's where collaborating with the national labs is really helpful because they have access to data sets that at just a research institution you don't have access to. So we're then able to run this analysis and generate plots here where we're looking at, for this energy storage system, the storage size, it's kind of its maximum power relative to its storage size, and then how it changes the number of startups that this generator would need to undergo, and it changes the mileage or how much the generator would need to change. And what was really interesting in this analysis is we found the energy storage didn't help the overall economics of the system. But what it helped was reducing these numbers of startups and reducing this mileage. And this is really important if you think about fossil energy as a bridge fuel, where there's carbon capture that's going to help meet global climate while still having the flexibility that comes with fossil fuel. And designing these carbon capture systems, you don't want to make them very dynamic. There's so many engineering challenges. And this is the real benefit of storage, because if you need to turn the unit on and off less, or it's changing its operation less, that really simplifies the design of carbon capture. And that was a really cool thing that came out of this analysis. All right, so this is kind of an example of breaking down that barrier and thinking about coupling detailed process models with detailed grid models. And now I'm going to talk about going a step further and pivot to another project that's related, dispatches. And here we're thinking about taking that information from the grid simulations and embedding it in process design. So the workflow I kind of described so far is a price taker workflow, where we took some historical price data and then we fed that into an optimization model where we could design the optimal size of the system, the optimal sizing of the energy storage. And here the really big assumption is this historical data is representative of the future. And by introducing this system, you're not going to disrupt the prices. And if you're an economist, you like to make this argument and say, well, if this new technology is really small, it won't have a really big impact. And this is the prevailing assumption. We also have some capability to take these and model uncertainty and kind of add some uncertainty aspects to this. But what I want to focus on is a totally different approach, where we're going to explicitly model the market interactions and embed them into the systems design. So what we're going to do is run a really big simulation campaign with Prescient, and we're going to perturb one of the generators and understand how changing one resource in a larger system changes the entire system. We're then going to use machine learning to build these surrogate models that we can then embed in the optimization. All right, so how did we do this? We set up about 64,000 simulations over a year for this test grid system, where we replaced one generator, and we varied a bunch of characteristics that are used at the grid level to model a generator. We then had a really nice simulation library, and in this simulation library you can look at things like the distribution of revenue and the number of times that you've shut down. And we were able to see that, yes, changing one generator can change the operation of everything in the system. depending on the size and the characteristics of the generator. We're then able to take all this data and fit surrogate models or machine learning models using one package, Elmo, that gives algebraic models, or Keras and TensorFlow, which gives neural network models. And what we want to do here is predict how the revenue changes and how the number of startups change as we change the characteristics of the generator. So this is a generator, it has to participate in the market. How does the market outcomes change as we change the design characteristics? We're then able to take these surrogate or these machine learning models and embed them in an optimization problem where we want to maximize the revenue of the generator minus the cost. So again, economics drives everything. Constrained by mathematical models for the process, these bid rules or the market rules, and these surrogate models for the revenue that you get from the market, and the dispatch. So how many hours in the year are you dispatched at full capacity, how many are you off, how many are you at min, etc. Oops. One second. But what we got is this really cool result. So what this plot shows is the marginal cost of the generator. We kind of change it from $5 per megawatt hour to 30. Five is really small. This was just kind of show how the model works. And the revenue. The colors correspond to a couple of different startup profiles in the data set. So one was a really fast, flexible natural gas turbine that uses peaking plant. Others were more baseline plants. And what the X's show is if we did a price taker simulation. What the solid data show are the actual market simulations, and what the curves show are our neural network surrogate models. So we see that our surrogate models actually do a pretty good job interpolating between these simulations. And moreover, there are several cases where the price taker's assumption is just totally off. And we can capture it with this alternative approach. All right, so the takeaway messages, and we'll have plenty of time for questions. So these integrated energy systems that combine a lot of different energy technologies, whether it be fossil or nuclear or energy storage or PV or solar or wind, they exploit synergies in these systems to provide more flexibility, or what I call dynamic flexibility. And this is really important in imagining an electric grid that has a lot of renewables, because you need to counteract that variability. And what we're able to do is take modeling and optimization to think about coupling the design, operations, and control of these integrated energy systems. And then we can take simulations of the electric grid, and we can also take models for the integrated energy system, and we can combine them together. And we can embed these market interactions captured with these machine learning surrogate models inside the IAS design, operations, and control problem. And with that, I'd like to acknowledge, support this is work that's a part of two really big DOE projects. Of course, the disclaimer. And with that, I would be happy to answer questions. Yeah.
I would like to ask, these optimization models are based on the current market conditions. And as far as I heard, Tesla's trucks are coming next year. And if they become widely available, those are sucking the power in gigawatts, megawatts like that. So is there a new model like that?
Yeah. So great question. I think maybe there's two parts. How do you think about the future? And then specifically, how do you think about a future where there's massive electrification of transportation?
It's not like the far future, it's very near future.
Yep. So one of the great things about working with the national labs is they have access to protected but real data for real electric grids. And they do have some predictions of how those will evolve under various policy scenarios. I didn't put it in this talk, but we've taken representative price data from those types of future-looking analysis, and we'll actually use it to compare different technologies with these future predictions. So the models are all set up to take that. There's also a lot of literature on that exact question of what is the impact of electrification of transportation, both on the demand side, but also on the supply side. And in that, you're going to have disruptions, both because you have to charge, but you have possibility for extra flexibility in that there can be incentive. Various regions and various like utility companies are exploring different incentive structures. Let's say that you have your Tesla plugged in at home. If you're willing to off-shift the time when it's charged, you get a lower price. Or even more aggressive policies, if you're going to allow the grid to use the battery, getting priced for that. So there's a lot of really cool work in that area, and I agree, it's really important. I'll do one, and then I'll come back to you, Scott.
This might be a little bit of a basic question, but I think on slide 6 or so, you showed like kind of the price over time, and I saw that it dipped negative briefly. So I get like with gasoline, prices can dip negative because someone has to like take delivery and like store like crude oil somewhere. But why in this case would you see electric prices dipping negative?
That is a great question, and it really helps. It gets at the complexity here. So, not shown in this plot are a bunch of transmission lines connecting all of the nodes. And those transmission lines have a finite capacity. At these nodes, there's also a variety of different types of generators. And some generators just can't ramp up or down that quickly. So you will get in scenarios where, where was the duck curve? This happens a lot on the duck curve, either when solar is coming online or going offline. You have a really big ramping event. And the change in demand is much faster than the ramping capabilities of some of the generators that are on. So you either have oversupply or undersupply. Then you will get places where the transmission constraints become active. So then you can kind of have this stranded power where you can't move it, and the generator can't move fast enough. And that's fundamentally what leads to these congestion events that then correspond to these negative prices.
So it's not like an increase in storage cost, it's a transmission cost that kind of comes into play.
Yeah, it's a transmission constraint and then a ramping constraint. Now, one of the cool things about integrated energy systems is because you're hybridizing various technologies, you can actually improve the ramping characteristics, and that helps on the ramping constraint side.
Could I add
Yeah.
to your response on that? So very specifically around here into Chicago, there's a fair amount of baseload capacity still, coal and nuclear plants. They will pay you money rather than have to ramp down because the wear and tear on the units is the issue. And so just to bring it home.
Yeah, yes.
So, I mean, if there's, my question is, you have this model now, you have developed it over the years. So now I'm going to flip it around and I'm going to ask you, if you wanted to, you could develop a strategy of going completely renewable by having strategically placed base loads, which are, let's say, nuclear or other such, and then completely take out the equation for reducing carbon dioxide and storing it or using it. So is that something that you can see as a strategy for providing some sort of insight for that?
Yeah, that's a great question. So kind of related to this modeling work, there's a class of models called expansion planning models, years into the future. And they ask the question of how does the profile of generation need to change in maybe 5-year increments to satisfy future demands. And these can be under a variety of policy scenarios. So there's a lot of really nice work in the literature taking those expansion planning models and saying, well, how does the profile need to change if you have a certain carbon tax, if you have a certain portfolio percentage renewables, or various other policy goals. I have anecdotally heard over dinner from a colleague that works on this that as that percent renewable gets higher and higher, the costs get much larger, and this is not a linear scaling. And he even shared with me that when you try to do the 100% renewables, the model doesn't converge, which means it's not you're not able to balance everything out. So this colleague's kind of very pragmatic view is like 90% is doable, 100% is really hard.
You don't need to go that far because you always need about 40% base load to at least, right? Mm-hmm. And the base load can be replaced. That's what I was getting at. Like it doesn't have to be. It can be some generic way of positioning it, but then you change the base load technology as you advance in your technological achievements as a society.
Yeah, and there's a whole class of modeling that looks at those types of problems. All right, probably last question for time, but yeah.
Time, yeah. So on slide 5, you show this these data traces for the 15 for 8 and 6. Sorry, this is.
Yeah.
You're showing these traces for the prices in the real-time markets. I'm curious how the fidelity in those measurements, 5 minutes, 15 minutes, and 1 hour, influence the outcomes from your models. So it's kind of, I'm imagining this like a molecular dynamics and quantum mechanics sort of thing, like your step size or your spacing that you're choosing. How that impacts your model, and I'm thinking of this in your models. Can you say with any sort of certainty, like if we look at this on 1-day scales versus 1-hour scales, how does it change the interpretation of your models?
Yeah, I would, the analogy to I think coarse graining in simulations of physical sciences might be a little overextended here.
Okay, all right.
What's happening behind the scenes is for every one of these levels, there's an optimization problem that's being solved at the grid level on how to rebalance everything. And what comes out of those optimization is what price do you need to pay everyone at each location. There's some really cool economic theory. So these are actually coming from kind of very scheduled re-optimizations of the entire grid. That being said, a really cool thing that we found is most people only look at the day-ahead price, the hourly scale, because getting this other data is kind of painful. And what we found is almost nothing is economic at only that time scale. And really, you're leaving so much money on the table if you're not looking at these faster time scales.
Just really quick, how common are these markets across the country? The day-ahead, the real-time? California is weird and it has 3 levels. Most places just have 2 levels, but they're pretty ubiquitous.